Okay, so we have talked about the equilibrium in all three places. We've talked about how does that equilibrium end up affecting the fact that there are different amounts of color, right? So in the water situation, very little of that equilibrium is happening where the calcium carbonate is dissolving. And so you end up with, in fact, a very little of the dye molecules being able to be trapped on the surface. You get a little bit more of this happening as you have more acetic acid because the reaction's happening there. And then as you have more acetic acid, because you have another equilibrium involved that can happen at a more substantial amount in that equilibrium, you get even more dye molecules that can attract to the surface. Okay, there's one more thing we haven't dealt with yet, and that's time, right? Back to chapter 13, back to kinetics. And I'm not going to ask you to do a super thorough kinetics analysis here. I can't. You don't have enough information. I haven't done controlled studies with different initial rates and things like that. You could. It would be a little complicated, but you could actually do it. But what I want you to be able to talk about in your project is sort of a generic idea of what's happening with the kinetics here. So let's remember, thermodynamics, and thermodynamics is what we've been dealing with for the last three chapters, 14, 15, 16, 17, yeah, 4 chapters, is basically telling us about equilibrium, right? So thermodynamics tells us if we wait long enough, what are we going to get in terms of concentrations? So that's our equilibrium. That's what we've just dealt with in the last few videos. Kinetics tells us how fast are we going to get there, right? So how fast does the reaction happen? And to some extent, that's the part that matters here, right? We've got really the same reactants in the last 2 beakers, but what we have is different concentrations of them. And so we have them happening at different speeds. And so in some sense, it's the kinetics that ends up mattering almost more than the equilibrium does for this set of reactions. So number 1, calcium carbonate dissolves, we get calcium 2+, we get our carbonate, right? But the question becomes, how does this actually happen? How do we get this reaction happening? How do we have these mechanisms? How do we talk about the kinetics? And so in order to talk about the kinetics, we really need to think about the physical mechanism of what's happening here. So this takes us back to chapter 12, our next chapter to integrate into this project. So let's think about what happens if we just have the water by itself. Now this picture is out of your textbook and it's for sodium chloride. It's not for calcium carbonate. But imagine that ionic substance is calcium carbonate instead of sodium chloride, okay? And so the way in which the calcium carbonate would dissolve in the water if it was just water is that water molecules are slightly polar, right? And so water molecules, as they come to the surface of the ionic substance, either the slightly positive or the slightly negative side of the water molecule comes near the ions and effectively pulls the ions out of the crystal, right? It's not just that the crystal's falling apart. It doesn't do that. It has that lattice energy holding it all together, right? There's an energetic advantage to the crystal being held together, and that's the lattice energy essentially, or the lattice energy is a measure of that, I should say. And as the water molecules come in, if they are strong enough, if the attraction between the either slightly positive or slightly negative side of the water molecule is strong enough to the ions in the crystal, they're going to pull them out of the crystal and dissolve them into the solution. And so you get these little clusters. For us, it would be calcium here and not sodium, and this would be a carbonate ion and not a chloride ion. But you get the idea, right? You get these little clusters where you have either your anion or your cation in the center, surrounded by a bunch of water molecules that are attracted to them. And those polar water molecules are what's pulling the ions apart, okay? And remember, we called that the hydration energy. It's the amount of energy involved in sort of getting these water crystals formed, right? So the hydration energy is that pull away from the crystal structure. The other side of it is the lattice energy. The lattice energy is the thing that's holding the crystal structure together, right? We know calcium carbonate isn't super soluble, right? It's not like sodium chloride. It doesn't just dissolve in water. And so what that tells us is that the lattice energy is pretty strong compared to the hydration energy. Okay, so the hydration energy is there, and those calcium ions and those carbonate ions that are pulled out into solution are being pulled out into solution because the hydration energy for those particular ions is great enough that there's an energetic advantage to doing it, but it can't be high enough that it's just breaking the whole thing apart, right? So the lattice energy pulls it apart. The lattice energy holds it together. The hydration energy pulls it apart. And so it tells us something about those interactions with what's happening in the water. Okay, so that's just water by itself, right? What if we take this into our acetic acid solution? If we're in the acetic acid solution, when the acetic acid dissociates, we also have hydronium ions floating around and acetate ions floating around, right? We've got the H3O plus, we've got acetate itself. The acetate is negative, the hydronium ions are positive. So instead of just having in the solvent just water molecules that can pull the calcium and the carbonate out, we also have these positively charged ions and these negatively charged ions. And hopefully you remember, positives and negatives attract, right? So if I have a hydronium ion that comes near the surface of my calcium carbonate, it's going to be able to pull out that carbonate ion much more effectively than just a water molecule would, right? Because it's positively charged. The water molecule has a little partial positive. Hydronium itself has a full positive charge. And so it's going to be a lot more effective at pulling out that negative ion. If I get acetate ions near the surface, they're going to be a little more effective at pulling out that calcium ion into the solution. And so it's going to be easier to get those things into solution. These charged ions are going to be better at it than just water itself is. And so if we look at that overall reaction that we had, and this is really just that first overall reaction for the acetic acid solution, not worrying too much about the production of the gas right now, so I'm sort of simplifying and just dealing with this one. We get this overall reaction where the calcium carbonate is basically being dissolved by that acetic acid, right? It's pulling the calcium out, it's pulling the carbonate out, and it's pulling it out strong enough that it actually go ahead and gives that proton to the carbonate. But this is our overall reaction, right? This is not a mechanism. Go back to chapter 13. We care about mechanisms if we want to talk about the kinetics. And so if we're talking about the kinetics here, what we need to concern ourselves is, okay, what's the mechanism, right? I don't literally get an acetic acid molecule bumping into the surface of the solid, and then it suddenly breaks up and turns into these products, right? Even from any logical standpoint that we've just talked about, that doesn't make sense. Because the acetic acid is going to dissociate, and it's going to be those dissociated bits that are going to be able to pull the calcium carbonate off of the surface. And so if we think about this I'm just going to totally admit, this is a reasonable mechanism. This is not necessarily the mechanism. But if we think about this from a reasonable mechanism standpoint, we can think about it as being a three-step process. And that three-step process looks exactly like the three reactions that we just added together in one of the previous videos. So calcium carbonate would dissociate a little bit into calcium and carbonate in our overall water solution. We would then also have our acetic acid, which is going to dissociate into some acetate ion and some hydronium ion. And then we've got that carbonate reacting with the hydronium ion there. This is definitely not a perfect mechanism by any means, but what it's going to allow us to do is to think about the rate limiting steps in a way that helps us make sense of what's happening between the second and the third container. Okay, so let's think about how this goes together in terms of a kinetics argument. So if this is our potential mechanism, we've got three steps along the way. And again, this is just a potential mechanism. I'm not saying for sure that this is the mechanism that's happening, okay? But if this is the mechanism that we're thinking about, we could think about either step 2 or step 3 being our rate limiting step. If step 2 or step 3 is our rate limiting step, then the concentration of the acetic acid is going to be part of that rate law. Right? So if step 2 is our rate limiting step, we've got acetic acid here that's breaking up into our acetate ions and our hydronium ions. If that is rate limiting, then the concentration of our acetic acid is clearly going to be important in the rate law, right? If the third step is our rate limiting step, and so getting any carbonate that has dissolved from the calcium carbonate to interact with the hydronium ion, if that's our rate limiting step, those two things finding each other in solution, then again, this concentration of the hydronium ion is going to be part of the rate law. Well, if the concentration of the hydronium ion is part of the rate law, the concentration of the acetic acid is going to matter also, right? And so if we think about that as our rate limiting step, either of these two things, actually 2 or 3 as our rate limiting step, then the concentration of the acetic acid is going to end up mattering in terms of that rate law. And so we don't have enough data to determine which step is the rate limiting step, nor is this probably exactly the mechanism, I'll be totally honest. But either way, if in our rate law, the concentration of the acetic acid is part of the rate law, then as that concentration goes up, the rate of reaction would also increase, right? So the more acetic acid I have, the faster this reaction is going to happen. The faster the reaction happens, the faster we get towards that equilibrium, the more dye is going to be able to integrate into the surface of the eggshell, right? Because we have more of that this overall reaction essentially happening. I shouldn't say more, it's just happening faster. And so we have more of the calcium carbonate per unit time, if you will, dissociating, and more of it resociating back into the surface. Okay, so if we have the same amount of time in both cases, more dye molecules are going to be trapped on the eggshell as long as we have higher acid concentrations. And you could probably come up with a different mechanism that would make sense, that would give you the same kind of answer. But effectively what we're seeing is that that concentration does matter, right? We get a darker color the more of the acetic acid we have in the solution. We had a really pale color when there wasn't any, right? I mean, this is not a fair mechanism for just water, but and then it gets darker as we have more acetic acid content and a higher concentration in those cases.